let us get started with this module. We are going to deal with multi-layer perceptrons. In perceptrons, we realized how through linear decision boundaries we can solve the pattern classification problem. But if we are interested in nonlinear discriminant boundaries for multi-class separation problems, then we will have to go with feed forward directed graphs called multi-layered perceptrons. So, let us get into the details of the multi-layer perceptron, and we will see how we can construct such networks, arrive at the derivation of the backpropagation algorithm, which is based on the multi-layer perceptron architecture. We will study different modes of operation of this algorithm, that is batch mode and online mode, and we will see some of the practical ways in which we can get this network to work. Okay. So, here is a schematic of the multi-layer perceptron. We have inputs here which are x1, x2, so on till x m0, right. This is without the bias, but we can have the bias and other details. As I get into the details of the algorithm, I am going to be more precise, but here let us assume at the moment that we have inputs x1, x2, so on till x m0, and the 0 indicates that it is the first layer or layer 0. Now, from each of these inputs we have connections. So, these are connections in the form of directed graphs or directed edges, I would say, that connect the inputs to the neurons within the next layer, and we can have such layers and we call them hidden layers, right. So, this is layer 1, similarly you have layer 2, layer 3, so on. You may have the L minus first layer followed by the Lth layer, which comprises of the outputs. Now, if we think through, we can have connections from every node to every other node, right. In the most general form, we can have a fully connected network, that is, a fully connected network has connections from every node or neuron to every other node or neuron. In the neural information processing nomenclature, neurons are even referred to as processing elements. This is another small detail. A neuron is also referred to as a processing element, and in this case it is a nonlinear processing element. Now, coming back to this architecture, so we have connections from every edge, connections from every node to every other node in the form of these directed edges, because there is flow of information from one node to the other node, therefore, we have these directed edges. And at the outputs we have a bunch of nodes where edges will terminate at these nodes. Okay. So, we can have this cascaded connection of layers of neurons that form the basis of our network, right. And since there is no feedback from one node to the other node, it is a feed forward network. Now, let us delve into the details. I have given you a bunch of errors here x1, x2 so on till x m0, right. Similarly, we can have different number of neurons within each layer. We can have different number of neurons within each layer. Layer 1 can have m suffix 1 number of neurons, layer 2 can have m suffix 2 number of neurons, so on and so forth. The last layer can have m suffix capital L number of neurons. Okay. This is very flexible, we do not have to be restricted by the number of neurons. Now, our goal is to formulate a criterion for the error. So, our error vector which is given by E is vector y minus vector d, where y is the stack of all the outputs y1 to y m suffix l, and each of these outputs have a corresponding desired response which is given by this vector d that corresponds to y1 through y m suffix l. So, how does this work, right? Your y1, y2, y3 so on till y m suffix l can be computed based upon the connections within the network based on the inputs. Similarly, based on the inputs we can also have a desired response, right, and that could be this vector d. A good example would be, imagine I give you the image of a cat, maybe in a certain orientation you capture the feature vectors, and those vectors could be x1 till x m suffix 0, right, and the desired response for a cat can be something like a vector which is 0 1 0 1 0 0 0, something like this. This could be a cat, and this y can be some real values r1, r2, r3, r4 dot dot dot, right. So, this is an example or illustration how one would think about the mapping between the output vectors and the desired response, and this is the basis of supervised learning. Okay. Now, here is the notation for the signals that we can think of. The bold blue edges stand for functional signals, that is our legend, and the error signals are denoted by these dotted lines, directed lines going from one node to the other node. At this juncture you would be very careful to sort of imagine why I have this error signal going backwards, right. If you are a little savvy, you will understand or you will see that when we have to compute the signals y1 through y m suffix l, we have to go through the feed forward paths, that is all the way from the inputs through the set of hidden layers to the output layer, and that is how we have to do the computation. But when we measure the outputs and subsequently the error, it will be at the last layer, and from the measurement of the error that we have in the last layer, we have to propagate the error signals all the way backwards from the last layer to the weights that are connecting from the input to the first hidden layer, right. Otherwise, how could we adapt the weights? This is a very important principle. So, therefore, we illustrate this through these dots, dotted edges and straight edges. Okay. This is sort of our legend for the signals. Okay. Let us go forward. Now, let y suffix j of n denote the function signal at the output of neuron j in the output layer, right. At each neuron in the output layer there is a functional signal and then a corresponding desired response in terms of an attribute or a coordinate, right. So, let us denote y suffix j as the functional signal and d suffix j as the desired response or desired coordinate, right, desired attribute slash coordinate of the vector d, and you know what y suffix j is. Now, the error e suffix j of n is d suffix j of n minus y suffix j of n. Okay, this is how we formulate the error, because it is just a deviation between the desired and the functional signal. Now, we formulate the instantaneous error energy. It is instantaneous because this is at time n, this is at time instant n. And you have to be mindful that this is a discrete time step. So, therefore, we write it is a discrete time instant n, and we treat this as half e suffix j square n. So, you may again wonder why this half. So, when you take derivatives, when you take the derivative of this instantaneous energy, you just get the error directly, right. So, therefore, that when you take the square, when you take the derivative, the 2 will appear out and the half and 2 will cancel. That is the reason why we want to introduce this half. This is a sort of normalization. And then when we take the square of the error, we do not care about its sign anymore, which is also a very important criterion when we have to think about techniques that are based on quadratic optimization. We do not care about the sign as long as we value the magnitude given by the square of the signal. Now, this is a very basic setup. Okay. From this we have to compute the energy, that is the error energy over all the neurons in the output layer, right. We have to compute the error energy that is instantaneous over all the neurons in the output layer, and this is given by this quantity E of n, which is 1/2 sigma j belonging to C, where C is a set of neurons in the output layer, the summation E j square n, right. You have the instantaneous energy, this is our instantaneous energy for neuron j, and if you sum this over all the neurons in the output layer, we get the sum total of the error energy, and this is given by this quantity. Now, you may question, does it end here, right? No, because this is for one particular sample. We have to look at all the n training samples, capital N. The small n stands for the discrete time step and capital N stands for the training examples or training samples or feature vectors that you may call, and we will have to average this error energy over all the n training samples. So, therefore, we get averaging it, we get 1 upon n. So, this quantity is nothing but 1 upon n summation n equals 1 to capital N E of n. So, this is how the averaging is done over all the training samples. So, now we have formulated sort of a metric, a performance metric for the training error, right. So, we have formulated a performance metric or a criterion for the error, and we have to minimize this error with respect to the parameters of the network to get the optimal estimates of those parameters, so that our network has learnt the data statistics. This is an important thing. Okay, I hope you have grasped how to formulate the metric at this moment. One important note before we get to the next slide is the following, that this is a quadratic cost, this metric is a quadratic cost, and we want to adopt this criterion so that it helps simplify our algebra and it makes the mathematics easy. That is, we can derive a good training rule from this, and this rule hopefully in some sense is unique. Okay. This is one small detail, and you may also question the mode of operation, how we want to update the neurons. We will discuss that criterion also when we get towards the operation of the algorithm. Now, there are two modes for learning. One is the batch mode, other is the online mode. Let us see how these two are different. I will start with the online learning because it is easy, and then I will get into batch learning. In online learning we adjust the weights for every tuple xi and di presented to the network at time instant I. So, this is the feature vector that is presented to the network, and this is the desired response. I will call this a vector because it will have different coordinates. Okay, so, this is presented to the network, and the network has to learn this, and the weights are adjusted for every tuple, that is every time instant I. For every example that I present, I learn the weights of the network. You may even wonder why this is done like this. Is easy, online learning is easy. We will discuss different pros and cons of online learning and other learning methods, but you have to understand that the updation happens at every time instant. We have the other mode of learning, which is the batch learning. In this case, the adjustments to the synaptic weights are performed after all the n, capital N data points in the training set are presented to the network. So, in one pass you present all the n data points in the training set to the network, then the synaptic weights are adjusted, and this process continues on an epoch by epoch basis. Okay. This is important, on an epoch by epoch basis. So, one epoch has all the data points presented to the network, and then at one shot the weights are adjusted, and this continues, and maybe you could shuffle the inputs and then again present it to the network if you are not dealing with algorithms that are spatio-temporal in nature. But as long as you do not worry about the time order, you can shuffle and present it to the network, right. So, these are two different update methods or learning methods, and each one has an advantage or disadvantage if you think of. So, this begins with the next natural question about pros and cons of batch learning versus online learning, right. Let us discuss with the batch learning first. So, the batch learning, the advantages are as follows. First, it can provide us with an accurate estimation of the gradient vector towards convergence, because the network somehow has seen all the examples or all the samples or data points within one epoch. So, therefore, you have sort of an average error energy within that epoch, and then you are kind of estimating the gradient based on that, right. So, it has a better estimation than the online estimation, because in online you are doing it per sample basis. So, it could be noisy, and you may not get sort of the mean captured here, the mean energy, error energy captured here. Second, batch learning lends itself to parallelization of the learning process. This is very important, because it is the same error energy, right, over, if you think about this, it is 1 upon n e suffix n for all small n equals 1 to n. This is how you are averaging this error, and this you can split into different engines, and you can learn each of these engines individually. So, this can lend itself to parallelization of the learning process. You cannot do this for online learning, because you do not have this average error energy captured over all the training samples, and therefore, you cannot do this parallelization process. What about the cons? Batch learning requires huge amount of storage. So, it is demanding on the storage requirements, and typically these days in AI applications, having a million records or 10 million records or a billion records, possibly that is sort of the criterion, right. You have huge amount of data, and we want to learn the data statistics. So, therefore, storing all this data and storing all these weights, and then being able to process these can be quite demanding in terms of storage requirements, and no wonder people go with GPU based computation or cloud based computation for these big data applications, right. And this is one of the major reasons, which also is in a way good, because people can think about algorithms that can work with parallelization and distributed kind of mechanisms to develop better algorithms that can overcome this storage problem. Now, let us get into the details of online learning, right. I discussed how online update is done, and we saw that the online update is done on a per sample basis, that is, you are given the desired vector and the input vector, and then you want to learn the weights at every time instant. So, there are pros and cons of this approach. The pros of online learning, it can track small changes in the data, right, because I am updating every step. I can track these small changes. I can figure out if there is a huge anomaly between what my stored weights in the network are versus the data that can change drastically how the behavior of the network is. So, I can track small changes in the training set. One can make use of redundancy in the data sets. This is very important, and if there is huge amount of redundancy, I can throw away that feature vector, and I can save my time, I can save my storage cost, etc. So, I can do that in online learning, but I cannot do it in the case of batch learning, because I average everything out. It is easy to implement. I think possibly this is the single most reason this is the single most good reason to adopt online learning, because it is easy to implement. So, these days neural network applications are being explored towards hardware, and particularly when you have to think about hardware constraints, ease of implementation becomes very important, because hardware resources are costly, there is power, area and all these implications. So, therefore, we want to have easy rules that we can implement within the systems, and this is one single most reason where when we think about neuromorphic systems, that we have to go with online learning. Cons: as we saw, parallelization is not possible, because we just have one sample and then we are updating the weights based on this sample, and we are doing this per sample basis. So, every sample that we get, we make an updation to the synaptic weights. So, therefore, we cannot parallelize the system. And another detail is we need to do ensemble averaging over large initial conditions. So, this is a sort of a detail that, because the gradient is noisy and we are updating the gradient at every time. So, if we were to get a good estimate, then we will have to do averaging over large initial conditions, different initial conditions. So, while this is a detail, may not be of much of an importance, the other pros and cons that I discussed, they have immediate consequence into the design, analysis and implementation of the algorithms, be it hardware or software, right. So, we will proceed further from this step. We will stop here.